Okay, so I'm going to explain a couple of things here that a lot of folks had some trouble with on the torque and center of gravity experiment. Um, it might get a little harder to hear because I'm going to have to step away from the camera, so you might have to turn your volume up some. Okay, so in part three of the torque and center of gravity experiment, and let's see, part three, step three. Here's the setup, okay? So you've got two sets of weight hanging here, balancing out the meter stick. And so it asked you to find all the torques in this setup and see if they balance out, right? So what all torques do you have? We're assuming that the axis of rotation would be right here, would be the actual fulcrum point, okay, which would probably seem like the natural place to pick it, right? So here's the axis of rotation here. It doesn't have to be there, which we'll see in the next step, but we're going to say the axis of rotation is here. We're going to use that. So, okay, so this mass on your left, it's creating a torque. So the weight that's hanging here, you've got that, and then the moment arm or the distance would be from where it's hanging to the axis. So right here would be your distance, okay? So now the x distance on the stick, you read that from the markings in the stick, but then the distance we're talking about now is right here, from where the weight is hanging to the axis of rotation, okay? So that one would tend to make it turn in a, as you're looking at it, I have to think about this, counterclockwise fashion like that, right? So this one would make it turn counterclockwise if something pushes that way, all right? Now on the other side, you've got this mass here, okay? So there's this much weight. It's not the same amount of weight as that over there. So the moment arm there would be from where the weight is located to the axis. So this distance right here, that's your R, your moment arm, right? Okay, so you've got that one. Now you've also got another torque, which is sort of a hidden torque, and that would be from the weight of the meter stick itself, right? So the weight of the meter stick itself would be, we can treat it as though it were all concentrated at the center of gravity, which would be around here at the 50 centimeter mark, okay? That's where you would expect it to be, because that's halfway across. I think actually it was 49.5 or something or other. But anyway, I'll call it the 50 centimeter mark just to make it easy. So the 50 centimeter mark, if you could sort of imagine like an invisible weight hanger hanging there, it would be like if you had however many grams the stick weighs hanging right there. Okay, so that would also be a force. And its moment arm would be from the center of gravity to the axis of rotation. Okay, and that tries to make it turn clockwise, which this one does too. So anything on this side pushing is going to make it turn clockwise. Okay, so you've got two clockwise torques and one counterclockwise torque, this one here. Okay, so they balance out. You figure out what they are in that problem, and when you add them all together, you should get something very small, close to zero compared to the size of the original torques. Okay, now if you didn't get something small, then that should have told you right away something wasn't right, because this is all balancing out, right? There's no net torque because it's not turning, maybe just a little bit from, error sources, but the total net torque is zero because it's not spinning around, right? So if you should get total torque to be a small number compared to the individual torques, okay? Remember, that's relative. We were talking about the size of an atom or something. That could be a huge number, but you got to think in relative terms. A small number compared to the component numbers, all right? Okay, so then in step 4, what it asked for was the upward force operating at point C, okay? So you've got to think about this a little bit. It's a little simpler than you probably might first think. So we're not worried about torques for the time being. Let's just talk about forces, okay? So what are the forces on the stick? Well, this one, these two weights hanging here, those are forces downward on the stick. And its own weight is also a force downward on the stick. So that's 3 of them, all right? So the stand, the fulcrum, is actually exerting a force upward that is equal to the sum of the 3 downwards, all right? So in other words, this is actually exerting a force up, and that would be equal to this force added to this force added to this force. Or maybe saying it another way, that total force upward that this is exerting would be equal to this weight plus the weight of the meter stick itself, okay? So that was the total force acting at point C. Now in step 5, what they asked you to do there, okay, this is where it gets a little weird, and some folks got a little confused on this. It is a little weird, I suppose, but it's valid physics. What they said there was, okay, this is not going to be the axis of rotation anymore. We're going to treat the zero end of the stick as being the axis of rotation, okay? Not changing anything physically. Same setup. Nothing has changed at all as far as physically, tangibly is concerned. Nothing has changed. But what we're changing is where we consider, in theoretical terms, the axis of rotation to be. And we can consider it to be the end of the stick if we want to do that. Okay, that might seem a little strange because you would probably naturally think of this as the axis of rotation. But if the thing isn't turning, then that would mean torque about any point would have to be 0. Okay, it's just sort of a matter of bookkeeping. Okay, so now you look at those 3 forces we had originally, these 2 and the weight of the stick itself. Okay, so they're all still there, but now if we treat this as the axis of rotation now, the end of the stick, then the forces are still there, but the moment arms of the torques they create are going to be different. So now the moment arm of this force, this weight hanging here, would be from there to the end of the stick. Okay, the moment arm of this force would be from the end of the stick to where the weight is hanging, okay? Then the weight of the meter stick itself, okay, that's acting here, so its distance would be from here to the end of the stick, right? Okay, so your torques have different distances now, all right? And when you look at it this way, they're all actually making it turn clockwise. You have to sort of imagine like if there was a hinge here and the stick were attached to it and it could swing around here. Well, all of those would be making it tend to turn clockwise about that point. Okay, now here's the really weird thing that happens. Now you've got a 4th torque that you didn't even have before. Okay, what's going on now is this, the stand, the fulcrum, is creating a torque now because it's like, okay, if this pushes upward, it's basically trying to turn the stick like this, okay? That's what it's doing. If you think of this as the axis of rotation, the stand is actually trying to turn it around counterclockwise like that is what it's trying to do, okay? So that torque is the only counterclockwise torque, and it ends up counteracting all the others, okay? So now you've got 4 torques, all right? Now that might seem a little strange. How do you get another torque that you didn't have before? And that just comes down to the bookkeeping. If you choose this as your axis of rotation, that's a smart thing to do because it's less work. Because the R distance, the moment arm, is 0, and so there's no torque at all. So that was the deal on that. Same physical setup, but this deal of the, this creating a torque that way, or I should say like that. Okay, that's what I think a lot of folks fail to think about. All right, so that's the deal on that. Now for the next part, you might have to, I'm going to be closer to the camera then, and so it might be louder, so you might get ready and turn your volume down, okay? Okay, so now I'm going to talk about question 1 in the question section, the first question about the baseball bat. Several folks missed that, not as many as missed the change of axis thing I was talking about before, but a few people missed this. So we're talking about a baseball bat, trying to find the weight of the bat, and we're limited to certain equipment. Okay, now the question said you had a knife edge to use as a fulcrum. Okay, some folks didn't quite understand what that meant. Okay, when you say a fulcrum, the fulcrum, all that is just an edge that you could sit a beam on, okay? Like with the meter stick, when we were doing with the weights hanging on the meter stick, that black upright stand was the fulcrum. The fulcrum doesn't include a beam to hang things on. You've got to have, that's different. There's the fulcrum and there's the beam. The beam sits on the fulcrum. Okay, now in this question 1 with the baseball bat, what you do is you actually use the bat itself as a beam. Okay, so the first thing you can do is on that first diagram on the left there, what you're doing is sitting the baseball bat on the fulcrum, on the knife edge that you use as a fulcrum. And just by trial and error, you could just try different positions until you find just the right position where the bat can balance on that knife edge. Okay? So that would mean that location must be the center of gravity. All right? It would have to be. So once you find that, you can note that location. You can get a magic marker or something and, mark it. And so then you know where the center of gravity of the bat is. You still don't know the weight of the bat, but you do know where the center of gravity is at this point. Okay? Now, the diagram on the right, that's where you use the 1 kilogram weight that it mentioned. And you could do something like what is shown in that diagram on the right. You can tie the 1 kilogram mass to one end of the bat and then rebalance things. It wouldn't work if you left the bat sitting at the center of gravity. It would have to be somewhere else. So it would have to be somewhere in between. So on the left side, you've got the 1 kilogram weight hanging on and pulling down, creating a torque that would tend to make the bat rotate counterclockwise. And so then on the right, you've got the weight of the bat itself. You see that vector, that arrow pointing down. Okay. So how do we know it's there? Well, that's because we made a mark where the center of gravity is in the first step. So we know that the weight of the bat is concentrated, or we could treat it as if it were concentrated right there. Okay, and so then the knife edge is somewhere in between. So if we had a measuring tape or ruler, meter stick or something, we could measure those distances, and it's fairly simple really. It's just from there on anyway. It's just your 1 kilograms on the left times the distance of the fulcrum. Okay, that's one torque. And then the other torque on the other side would be the weight of the bat itself times that distance from the center of gravity to the fulcrum. Okay, some people got most of that but didn't say anything about how do you know where the center of gravity is. So you would have to do that first step. But anyway, that's how you do it. Okay, alrighty.